So today we are going to discuss about merge sort. Okay. So merge sort is a divide and conquer algorithm that recursively split an array into two halves. Means first duty is to um, divide the array into two parts. This is part A, this is part B, and this divide thing will going on until unless we get individual element. There is nothing to divide further. And in the second part, it merges the sorted until each array contains only one element which is considered sorted. So until unless it is sorted, it will keep merging. So first is the divide part, which will be dividing the array into array and then further arrays. That will be called the divide part. And the second part is the merging part. Merging part will continue until unless all that divided elements, single elements, getting sorted. So merging process compare elements from the two arrays, placing the smaller element into result array at each step and continues until the elements from the both arrays are merged. This process ensures that the entire array is sorted as the subarrays are combined. So merge sort consistently operates with the time complexity of O n log n. So merge sort time complexity is O n log n, making it efficient for the larger data sets. So it's a quite efficient algorithm. So here you can see that so this is the so initially how it will start. So we'll be having a left pointer. This let us call that as left, and we'll be having right pointer. Let us call that as right. So left pointer. Let's say the index is 0, 1, 2, 3, 4, 5, 6, 7 elements are there. 1, 2, 3, 4, 5, 6, 7. Indexes are up to 6 because we have started from the 0. So first you have to find this left pointer, which is L, and then you have the right pointer, the last element. So left pointer index is initially 0 and right pointer index is initially 6. What you have to do, we have to find the middle element. Okay, we have to find the middle element. So first you have to find the middle element. You can see that this middle element is nothing but left pointer plus right pointer by 2. Okay, so left pointer index is 0, 0 plus 6 by 2, which is equal to 3. Now in this case, what we are going to do, we are going to, if it is, let's say after addition of left pointer plus right pointer divided by 2, if you get an odd number, I mean it's a fraction, if we get a fraction numbers, then we will take the floor value of it, or you can even take the ceiling value of it. But whichever you are considering as the first partition, you maintain that process for the remaining partitions also. So in this case we are having index is 3, that means 0, 1, 2, 3. So up to 3, element 3, it will be the left array, and 9, 82 and 10 will be the right array. It can go either way also. You can consider first 3 elements as a first array and second 4 element as the second array. Only thing is that once you fix it in the first iteration, let it be continuing for the remaining partitioning also. So that means every time if you consider it is still a floor value, then continue with the floor value itself. But here in the initial case it is only 3, so we don't have any fraction, so there is no problem. Now what will happen, we will be having recursive calls of first merge sort. So merge sort, it is left pointer, this is left pointer, and then this is middle element M, and let's say this is M, and so this will give a call, first call, that means left pointer index is 0, 1, 2, 3, up to this one call will be there, and then this call will again further produces more recursive calls. Okay, so again you can see that the mid pointer, in this case the left array, in the first partitioning will be 0 plus 3 by 2, which is equal to 1.5. So 1.5 floor value will be because we decided that we will take the floor value which is equal to 1, that means 0 and 1, and then 2 and 3 is the remaining this thing. So middle element becomes 1. So 0, left will be 0 and this will be 1, like that. Okay. So fine. Now again 0 plus 1, 0.5, 1, 1. So 0 plus 1 will be 0.5, so 0, and then the remaining will be 1. So in the left sub array it will be like 38, 27, it will come like that, and the right sub array it will be 43 and 3, like that. Everything will be comes down to single element, and this part will be called divide part, which is nothing but partitioning the array, the given array, first half of the given array. Similarly, from here, the second part of the right subtree, we have started from this was our mid index, which is nothing but, this was initially our mid index, which is nothing but this one. So and then mid plus 1, that means 3 was initially mid, so mid plus 1 will be 4. 4 to 6 another call will go, that means this is 4, 5, 6 another call will go. So here also you can see that again 4 plus 6 by 2, this is 4th index, this is 5th index, and 6th index will come here. Okay, so here 9 and 82, again 9 and 82 will be partitions, and it will be 9, 82 and 10. So finally you will get this all, the elements of the array, given array, which is this one, as individual elements. So this part is called the divide part. Okay, divide part, partitioning part, and finally you get all the elements. Individual elements are there. Now the second part, so this is the first part. Second part of the algorithm is nothing but you will be merging them. So every time you divide it, you have to merge. So when there is no place to further divide, like in this case it is 38 and this is 27, we don't have anything further to partition. Now you have to start merging it in sorted. So that will be done by this array, left, middle and right. Okay, so initially 27 and 38, these two elements will be merged and sorted. So this is 27 and 38 is nothing but 27 and 38 will be as it is, only because 27 is less than 38, sorted all order, and the second half will be like 3 and 43. So this is also again sorted, and again this part 27, 33, 38 and 3, 43, this will be again merged. Okay, you have to keep merging it until unless there is nothing to merge. So when you merge this, what you have to do, like you have to find the minimum element from this subarray, you have to find the minimum element from this subarray. So it is 27 and 38 is nothing but 27, and minimum element from this side is nothing but 3. So you have to compare 3 and 27. 3 is minimum, so you put 3 here. Okay, then 3 is already addressed. Now among remaining element you have 27, 38 and 43, and among all 27 is the minimum, so 27 is placed here. Now among remaining element 38 and 43, 33 is the minimum, and then you have the second, you have the maximum element in this particular server is nothing but 43. So 3, 27, 38, 43 is a sorted order value coming from the first subarray. You can see this up to this much. So this part has become this after merging using merge sort. Similarly, from this part 9, 82 at 10, again this partition happens here, and then you get this again from 9 and 82. Who is the minimum? Which is the minimum? 9, and among this is 10 only individual element. 9 and 10, 9 is the minimum, so you place 9 here. So 9 is placed. Now 82 and 10, which is the minimum? 10 is the minimum, so you place 10 here, and then finally you place 82. Now these two subarrays which are individually sorted, but finally when you get the results, that means this part of the array has been sorted. So now when you merge further, it will be placing all the sorted array in proper location. So you can see that here from the first subarray minimum element is 3, from the second subarray minimum element is 9. So 3 and 9, 3 is the minimum, so you place 3 here, and then from 3 is addressed. Now among all these three elements, 27, 38, 43 and 9, 10 and 82, which is the minimum? 9 is the minimum, so 9 will be placed here. So 9 is addressed. Among 27, 38, 43 and 10 and 82, which is the minimum? 10 is the minimum, so you place 10 here. So 10 is addressed. Now among 38, 43 and 82, which is the minimum? 27. This is so here in first it is 3, then it is 9, then 27, 38, 43 and then 10, 82, which is the minimum? 10 minimum, 10 is done. Now 27, 38, 43 and then 82, which is the minimum? 27. 27 is minimum, you place 27 here. Now 33, 48 and 82, which is the minimum? 38 is the minimum. 82 and 43, which is, so in a 32 placed here. 83 and 43 and 82, which is the minimum? 43 is minimum, place it here, and then finally place 82 here. So this is a sorted order element. So this is nothing but will be done by the merge function. This function merge, okay? So every time. Now if you see this, what will happen exactly? So this is the index. So initial call is nothing but 0 to 6 in the merge sort. So 0 to 6. So that means this is a part. Then here merge sort. The left pointer, and this is the mid pointer. This is the first call. This first call again will give three more calls, because if you see the algorithm, it is this merge sort from left to middle, merge sort from middle plus 1 to right, and merge from left, middle and right. So every time you call merge sort, three functions will be called. First is this one, merge sort. First is this one, merge sort, then merge sort, and then merge. Okay, with this 0 and 3. Similarly, so, and then you can see here another call will be mid plus 1 to 6, that means 4 to 6. This is also raise three calls here, 4 5 5 6 and 4 4 6. Okay, and then finally you'll be having merge initially. So this, every time you have this merge sort call, three functions will be called merge sort, and then merge. So initially, so if you see this structure in terms of tree, it will be like this. So first it is 0 to 6. So 0 3 calls is here, 0 to 4 to 6 is there, then 0 1 this side, and then 2 1. Okay, so now it is like, if you see from the recursion tree perspective, so this is the recursion tree here. Recursion tree, if you see, so initially this is the midpoint is 3. So midpoint is 3 means 1 2 0 0 1 2 3. This has come to the left side, and then mid plus 1 is nothing but 4 5 6. Mid plus 1 is 3 plus 1 4. So 4 5 6 comes this side. Okay. Now again mid is 0 to 3, 0 1 to 3. So mid will be 1.5. 1.5 means 1. That means 0 1 0 1 comes this side, 0 1, and then 1 plus 1 2 and 3 2 3 come mid plus 1. That means mid plus 1 is 1 plus 1 2 2 3s. Now again this will be further partition, and then you get the individual element 38 27. This is the merge sort part. Okay, and then you have this merge function. Now here the merge function will be like what? Here the merge function is, you can see the algorithm here, it is nothing but left middle right. Okay, so left middle right means it is left is 0. Okay, here mid also 0, and the right is mid plus 1. So here among 27 37 38, 27 is the minimum, so sorted order things happens here. Okay, so this part, and then here similarly 43 and 3 is minimum. So this is left, yeah, so here if your algorithm, if you see left middle right, so left is nothing but 2, and middle and right is nothing but, left is also yeah, left is also 2. Here this part I'm talking about, middle plus 1 is also 2, and okay, so middle plus 1 is 2, and then right is this is the right pointer. Okay, so 2 2 3 will be, no, sorry, so here what is happening, left middle right. So here left is nothing but 2, middle also 2, and then right is 3. So these 3 will be sorted, 3 and 43. Similarly from this side also will come. So finally you have this and this. Okay, so finally you get these results as a merge sort. This is sorted output. So the time complexity, you can see this is nothing but a tree only. So for n element, for one element, if you want to do anything which is log n, and then for n element it is n log n. So final time complexity is n log n for merge sort. I hope you understood this.